Welcome back to our video module on quantum mechanics. Today we're going to continue our discussion of the WKB approximation by looking at tunneling. We've covered E is greater than V and E is less than V. The natural step is what happens if we combine both of them in the same type of graph. You can see what I've done below in green where I've sketched a potential profile where for some of the time your energy is greater and other times the energy is less than that potential profile. We've dealt with this before, but always with rectangular potential profiles. So for instance, we might have a potential profile that looks like this in pink. The question we want to pursue today is how is our evaluation of tunneling different when we use the WKB approximation to look at more innovative potential profiles? Let's do a quick review of tunneling, making sure we're on the same page, and then we'll wrap our head around this. One can imagine a free particle moving from the left to the right with some sort of energy as shown by the gray bar. We know that the wave function representing that free particle is going to come in with some sort of amplitude A, and some of that will be reflected. We called that amplitude B. In addition, there's some of it that will be going to the right with amplitude C through the higher potential region, some coming back with D, and finally some of that wave function will be transmitted on the right-hand side of the potential with F. And if you recall, we set up a ratio that was the probability of transmission, which was the magnitude of F squared divided by the magnitude of A squared. By using our initial conditions or conditions we knew about the energies, we were able to solve for the transmission. Let's move this out of the way and see what we can learn. Now we know enough about tunneling as it stands that we can probably draw a rough schematic of what the wave equation looks like. So this wave function shape should look pretty familiar. We see a high frequency wave function increasing in amplitude, wavelength increasing as E minus V decreases until the point where we see that E minus V goes below zero. At this point, we're moving into a exponentially decaying function, and the stronger E minus V, or the wider that barrier, the more decay we'll see. And finally, our transmissibility is that ratio between F squared to A squared. None of this should be any surprise. However, what we do notice is that all of our old assumptions and our wave function forms aren't applicable here because we're dealing with a potential shape that is not a simple step function. Now, just like before, we could set up equations for A, B, C, D, and F and go through the work of identifying boundary equations and initial conditions to try to find transmissibility. Or, since transmissibility is our main concern, let's just ask if there's a simple equation that tells us what it is. And in fact, there is. Assuming all the WKB approximation assumptions are true, we knew that F over A is e to the negative 1 over h integral of magnitude p dx. And in this case, our integral limits, a and b, define the location where e equals v, or in other words, where we really start to see that exponential decay. Sometimes we will see it like this, e to the negative gamma, where gamma equals 1 over h bar, the integral of a to b p dx. Now, before you get too down on this, taking a look and saying, well, everything acts the same, the only thing we've learned is we have this new equation, what have we really learned? I'd like to show you what we're able to do now. We're able to evaluate the wave function of bound and unbound states, and in particular, I'll give you one that should look pretty familiar to you at this point in your physics career. Here, I've drawn a potential profile that's very relevant when we start looking at nuclear forces. In other words, when we start looking at half-life and radioactivity. Thanks for taking this quick look at tunneling with me, and I look forward to seeing you on our next video.